Welcome to today's lecture on IoT. In this lecture, we continue our investigation of infrastructure components for IoT systems. So today we're going to talk about networking in IoT, related protocols, a bit of hardware, and networking infrastructure. So first, when we talk about networking, we need to discuss some basics. Some of you might have already seen this in a previous course on computer networks, but still, I think it's a good idea to revisit this information here. So in general, when we want to network computers, we have the choice between two modes of communication. One is circuit switched communication. So circuit switched communication works like the old analog telephone system. So essentially, you switch a exclusive line, a separate line between the two partners of a communication process, like the two telephones in a regular analog telephone call. And this complete line is exclusively reserved for these two communication partners as long as this communication process takes place. So no other communication partner in the whole communication system is able to use one of these partial routes here. So even if we don't transmit any data, so if we just call someone and it's complete silence on the telephone, we would still occupy that line. So this is obviously especially a waste of resources when we consider computer communication, where maybe, well, it takes a couple of seconds between requests to web servers because you look at web pages and then you click a link after you read a bit of a page and so on. So modern computer networks and even voice and telephone networks today are what we call packet switched. So packet switching means that all the data that is transmitted is chopped up, split up into small pieces, and these small pieces are then sent along with some identifying information like the sender and the receiver address, for example, uh, and they are sent along a common network, and they can share these network connections with completely different communication processes going on between completely different communication partners. So these packets really allow us to make better use of a network because packets are short. So we can use the capacity of a network better here. And this is what, almost every network nowadays is actually using. So when we look at networking, there is a standard model that is used for modeling almost all networking systems, and this is the so-called ISO OSI 7-layer model. So ISO is the International Standards Organization, and OSI is the Open Systems Interconnect, so they worked together to define a very abstract model of networking, and this abstract model of networking consists of all the layers from your application to the bits going on the wire. And this communication is split into several parts. This is here on the left-hand side of this picture. So on the bottom, we start with physical connections. This might be your Ethernet cable, but also some definition of a wireless channel for Wi-Fi, for example. On top of this, we have a so-called data link layer, which handles communication in a local network. So, for example, in an Ethernet, where all machines are connected using a simple hub or switch, but no router. On top of that, we have the network layer. So this really takes care of larger networks, how to get packets of information from one communication partner to the other. On top of that, again, we have transport. So transport actually models communication from one host to another host on the network. And again, on top of that, we have additional, sometimes optional layers. These are session. So a session might be something which you have used when you used an SSH or telnet command to log into another Unix machine. So a session starts when you start the SSH connection, for example, by just typing the SSH command in your terminal and then logging in. And this session ends when you log out from the remote machine again. Then we have presentation. So presentation takes care of common things that have to be agreed upon by the communication partners. That might include things like common character sets, for example. And finally, we have an application layer. So everything that's happening on application side obviously takes place in this highest layer. Now, this seven-layer model is very general and it fits very many networks and exists for like several decades. When the internet protocols were developed, however, the modeling was a bit more simple here. So essentially, we have a network access, which incorporates the data link and physical layers, as you see on the right-hand side, in one part here. So TCP/IP doesn't really care what's below the network layer. It's just provided, for example, by a device driver, and that takes care of local communication in an Ethernet, talking to an Ethernet card, sending, receiving packets, and so on. Then we have the internet layer, which is equivalent to the network layer in the OSI model. We have a transport layer, which is the same as a transport layer in OSI. And then everything else is just on application layer here. So as we are talking about IoT devices, with I, of course, standing for Internet, we will mostly talk about TCP/IP protocols in this lecture, because obviously TCP/IP is what runs the Internet. So the important thing is that TCP/IP protocols actually are not bound to any specific network technology, or we say they're network agnostic. And so they can not only be used with like Ethernet, but also with very many different technologies like Wi-Fi. And you can also run TCP/IP over Bluetooth, over Zigbee, over so many different protocols. As IoT devices mostly use wireless networks, we're going to concentrate on wireless networks for now. So wireless networks have a number of different properties. These are important for assessing typical characteristics like, how many stations can you actually realistically run in a single network, which latencies, which data throughput do you get, do you have any opportunity to have disturbances in your communication because somebody else is also using the frequency range. So a frequency range here is one of the important properties. And in general, we distinguish between unlicensed and licensed communication bands. So a band is just a technical term for a range of frequencies starting at a lower frequency and going up to an upper limit of a frequency. So we have this so-called ISM band. So ISM stands for Industrial, Scientific, and Medical Applications. This is a reserved band for these applications. And the interesting thing about ISM is that ISM bands can be used without acquiring a license. So you may be heard when 3G, 4G, 5G mobile networks were discussed in your country that, the operators that wanted to run a mobile phone network needed to apply for frequency licenses. And at least I know it from Germany, these were horrendously expensive, like in the billions of dollars for getting a frequency license. So the permit to use a certain mobile phone frequency range. If you needed to apply for such a frequency license, just for every Wi-Fi router and every Wi-Fi device, for example, you want to set up, well, that would be quite a bit of overhead. So Wi-Fi and other protocols operate in this ISM band, which has the property that you can use it without having a license. Obviously, the manufacturer of the device still needs to pass some certification to be able to use this range. Like in Europe, we have the CE certificate and additional certificates that enable a device to be used in Europe on a wireless network. But nevertheless, it's much easier than, compared to getting, your mobile phone operations running. So there are several frequency bands for ISM. I'm giving the European frequency ranges here. So there's a very narrow band at around 433 megahertz. So this is mostly used for simple radio frequency transmission, for example, from very simple sensors, usually without a lot of protocol overhead. Then there's a larger range between 2.4 and 2.5 gigahertz, and this is a very useful range because, this has enables a large bandwidth. You can have useful transmission distances over your network. And so this is used by quite a number of technologies like Wi-Fi, so 802.11, Bluetooth, Zigbee, and many more. Unfortunately, 2.4 gigahertz has another problem. It's also the frequency that is used in microwaves to heat up water. So, whenever a microwave is running in the vicinity of your wireless network using the 2.4 gigahertz band, then uh, it could just disturb any transmission because it would emit energy into this band. So it could disturb transmission of your wireless stations. So if you look closely at your wireless router, there's a large number of devices where you can actually enable a feature called, yeah, microwave interference. So it filters out some certain frequencies that are most, critical for interference here. And recently we have what's commonly called a 5 gigahertz band. This is between 5.75 and 5.875 gigahertz. So this is a higher frequency band, which today is mostly used just for high-speed Wi-Fi transmissions. On the other hand, we have license bands, so bands where you need this official permit by the state in order to transmit anything on these frequencies. And if you try to transmit without a license, if you're caught, this can have very hefty fines going into the hundreds of thousands or millions of kroners. So, just getting device for sending unlicensed on these bands is not a good idea. And we have a number of bands here. So on the 900 and 1800 megahertz bands, we have the old GSM digital mobile telephone system. So the 2G and Edge, the first real useful digital telephone systems for mobile phones. Uh, the 900 megahertz band is reused together with a new band at 2100 megahertz for the UMTS, so 3G. And then we have a number of bands between 800 and 2600 megahertz, which is used for 4G or LTE. And then we have additional features on 5G with even higher frequencies, 2300 to 3400 megahertz for 5G. And there's a very new technology called millimeter wave. So this just gives really the wavelengths of the waves going through the air. And this is running at a very high frequency between 24 and 29 gigahertz actually. Millimeter wave is mostly available in the US. I haven't seen any European installations, but I guess they will be coming up in the next couple of years. So when we are building a wireless network, we have the choice between two general modes of operation here. So these two different approaches uh, are based on the idea of, on the one hand, you have some stationary device, which is able to provide you with some sort of infrastructure and maybe connection to the rest of the internet. So this is what your home network might look like. You have a central Wi-Fi router, for example, that has an Ethernet connection to your internet provider and then provides wireless connections to whatever devices you have connected here. And this means all communication has to go through this Wi-Fi router. Without the router, the devices would not be able to interoperate to communicate directly. Now, of course, we have IoT applications, and we've seen some of these in the application examples that are out in the field. So you cannot assume the availability of any sort of wireless infrastructure here. So you have to create it yourself, especially when you have moving targets like a drone that wants to communicate. And for these systems, we have point-to-point or mesh networks. So there's several examples that are used in IoT. For example, Bluetooth provides what we call scaternets. Zigbee is in general a mesh network. And these are characterized by some features in addition to the infrastructure. So we don't have a central component that, for example, distributes IP addresses. So for point-to-point networks, we need ways to automatically assign addresses that do not conflict and still enable routing. We need methods to find other services and other devices on the network without having a central router. And of course, the important thing is here, a device can directly communicate with other devices without having to use a router in between. Nevertheless, you can still have a router as part of such a point-to-point network, which is just another point-to-point communication partner, but provides an additional service like forwarding packets to the internet. So the network technology used in IoT applications. Uh, is in general, as we've already seen, classified into two large classes. So we have, as we see on the bottom here, wired networks like Ethernet. We might have CAN bus in cars. We might have RS-485 for old industrial automation systems, but most of the systems are going to use wireless. And in wireless, again, we have three subclasses. One class is adopted from use in PC systems. So, of course, you all know Wi-Fi. Officially, this is called the IEEE 802.11 family of standards. So we've seen they're running usually in the 2.4 or 5 gigahertz bands, and they have a throughput between 2 megabits per second and around 300 megabits per second, maybe a bit more nowadays with advanced technologies in Wi-Fi 6. And we have another technology that also started in the PC sector, which is Bluetooth. And Bluetooth is able to provide you with mesh as well as infrastructure networks, both running in the 2.4 gigahertz band. Another approach to, that's infrastructure based, obviously, that enables you to network IoT devices is the use of cellular networks. So you have a mobile, phone modem essentially. Like the one in your mobile phone that connects your IoT device to the cellular network, and then you can run TCP/IP protocols over the cellular network, depending on how much money you want to spend. Between 2G and 5G technologies is possible nowadays, but note that some of the intermediate technologies like 3G were shut down recently in a number of countries, which has caught some IoT providers pretty unexpectedly. So they had to quickly, invent different alternatives. So there was, for example, a set of rentable bikes in Trondheim in Norway, and were connected using 3G networking. And the city of Trondheim just shut off 3G networking sometime around summer last year, without obviously notifying this provider of bike rentals. And so they had lots of problems really finding their bikes again because they were sending GPS positions using 3G. And as 3G was no longer available and they didn't have hardware for 4 or 5G, they were automatically falling back to 2G, which meant that the 2G channels were completely overloaded. So they had lots of problems really getting in touch with the bikes that were rented, figuring out where bikes were. So this was pretty much chaos for a couple of weeks there. And of course, with cellular networks, you always have the problem that you have a provider, and this provider wants to be paid for the cellular network services. So you need a SIM card, you need to pay for data transfers, which is, something different to all the other networking technologies we're going to talk about. And the final subclass of wireless networks we're talking about is low power networks, and these are very often specifically designed for IoT applications. And here we distinguish again between two classes. We have wide area networks, usually low power wide area networks to enable us to have small devices with little batteries or energy harvesting to communicate over a network, for example, LoRa, WAN. And we have short range and mesh networks like ZigBee, Z-Wave, and Thread. So one of the most commonly used technologies is, of course, Wi-Fi, or as we've already seen, IEEE 802.11. So this was intended to be a wireless network technology to replace wired Ethernet connections to enable mobile computing since around 1997. And Wi-Fi connections usually use an infrastructure mode, so you have your Wi-Fi router or access point in Wi-Fi terminology, which then provides network addresses, routing, and everything that's required to all the Wi-Fi devices in your network. There are also proprietary mesh solutions which work up to 1,000 nodes. We've linked one there, but there's no official standard for meshed Wi-Fi networks. Today we can have a range, depending on your antenna setup and so on, of up to 50 meter indoors, and depending on how you configure it outdoors, of course, a larger range outdoors. We've already seen that Wi-Fi originally used this 2.4 gigahertz ISM band. Now, also with more recent Wi-Fi technologies, we have support for 5 gigahertz with less disturbance by other network protocols here. Now, 802.11 is not just one standard, but there are at least, as last time I counted, 15 different compatible standards so they're mostly upwards compatible. So that means a more recent device is able to work with an older infrastructure, not necessarily the other way around. So one common problem you have when you have older Wi-Fi devices uh, is the security and encryption protocols. So there are different approaches to do this protocol encryption. So this is called WEP or WAP, and the old mode WAP or WAP1 is no longer secure enough because it used relatively short keys, which can easily be cracked nowadays with the computing power you have available in a PC. So this old WAP is no longer supported by more recent access points, which means that if you try to connect such an old device that only supports the old WAP protocol, WPA protocol, to a more recent router, that won't work. So you'd either need a software upgrade for your old device, or you need to lower security settings in your router if this is available, which is obviously not recommended. So here we have a problem, but in general, communication between devices works relatively well. And the most common Wi-Fi standards today are 802.11n from 2008. So these are theoretical maximum limits of up to 600 megabits per second. This still runs in the 2.4 gigahertz band. Then we have 802.11ac, which is already 8 years old, which has up to 1300 megabits per second in the 5 gigahertz band. And most recently, we have 802.11ax, which can in theory provide 11 gigabits per second and also uses an additional band optionally in the 6 gigahertz range, which is called Wi-Fi 6E. But note these are theoretical maximum numbers, so the real achievable communication bandwidths might be quite a bit lower depending on your circumstances. Another problem is, as we've seen, compatibility. So many IoT devices only support older Wi-Fi standards. So if you look at the very common ESP8266 or ESP32 devices, so very small, like 50 kroners microcontrollers with Wi-Fi and sometimes also Bluetooth, depending on the device. They only support the older standards B, G, and N, but none of the more recents. So these are still compatible for now with like authentication, security standards, and so on, but they might not be compatible with future standards, for example, a future encryption standard, WPA3. Right, so another technology, as we've seen, that came from the PC sector is Bluetooth. And Bluetooth was originally intended to be a replacement technology for low-speed cable connection, like your mouse and your keyboard and so on. So it's a set of short-range wireless technology standards. This is like Wi-Fi, a packet-based protocol, and this is using what is still called a master-slave architecture in the standard. Now, you might have noticed the discussion, of course, in modern times, calling such a setup master-slave is no longer appropriate. We only use it here because it's still in the standards, and the standards have not been changed so far. So what master-slave means is that there is someone controlling the communication, and the other ones are more or less clients of this system. So Bluetooth is interesting because it tries to avoid conflicts in this very crowded 2.4 gigahertz band. And it uses what's called a frequency hopping spread spectrum. So two communication partners, when they want to set up a communication, do not just agree on a fixed frequency range within that ISM band, so a subset of a frequency band, but they actually switch the frequencies relatively quickly, and they have a joint algorithm, obviously, to switch frequencies. So this means even if there is an interference between, for example, a Wi-Fi connection and a Bluetooth connection, this only lasts for a very short time because Bluetooth changes the frequency it's operating on very soon after, so in the range of milliseconds. This is very nice to use, but of course it requires agreement, so sender and receiver have to use the same frequency hopping scheme in order to find each other again. So this frequency hopping spread spectrum technology was pretty interesting. So it was already invented in World War II by one of the women who was a pioneer in radio and information technology, Hedy Lamarr. And they actually invented frequency hopping spread spectrum as a way to avoid people listening on to radio connections. Obviously, if you don't know the order of frequency hops here, so between which frequencies are switched in which order, then obviously it's very difficult to listen to a traditional radio connection. And yeah, this technology is now used indeed in Bluetooth, of course, with a digital connection, no longer with analog radios as in World War II. So Bluetooth is relatively low power, so it has a transmission power usually of only 2.5 milliwatts, which means the range is also quite limited, so usually around 10 meters, which is enough for just having a wireless keyboard or mouse, or maybe connecting your phone to your computer, but it's not sufficient to build a network that covers your whole house, obviously. Yeah, and the packets are transmitted in each of these in one of these 97 channels, so these channels are relatively narrow in order to reduce interference, so they have a bandwidth of 1 megahertz only. And we have, as we said, around a millisecond range for hopping. So in the standard, we have the definition that Bluetooth performs 1,600 frequency changes per second with a predefined hopping scheme. Of course, this hopping scheme is well known because all communication partners have to agree on the same scheme, so it's no longer used as a method to do encryption nowadays. It's just the same approach for a completely different use case. So in Bluetooth, you can have different network structures. So the base structure for Bluetooth networks is a piconet, and a piconet means that we have a designated master device. Sorry for using master again, but it's standard. And this master Bluetooth device can communicate with a small number of devices, a maximum of 7 devices in such a piconet. And a piconet is an ad hoc computer network using Bluetooth, so we don't need any manual address configuration like with Ethernet or Wi-Fi. This is something that happens automatically. And this clocking, of course, is very critical for the frequency hopping. So all devices in a piconet use a master clock that's provided by the master for, essentially is initiating and controlling packet exchange. Then you can connect multiple of these piconets together. And multiple of these connected piconets, as we've seen in the picture on the right-hand side here, can form what we call a scatter net. So a scatter net is, just essentially that some of the nodes in your piconet take over the role of a router and can forward packets from one piconet to another. And the sole information in Bluetooth is clocked according to some clock periods of 312.5 milliseconds and usually use a slot of 625 microseconds, which of course fits well with the 1600 frequency hops per second we've seen before. Two slots are a slot pair, so we have a request and response usually. And for simple single slot packets, what happens is that usually we have a distribution of time, so time multiplexing here. So in the first round, in the even slots, the master transmits, and in the odd slots, the master receives, so all the other devices can transmit. And of course, the slave devices do it the other way around. A more recent technology development is Bluetooth Low Energy, or BLE. So BLE is an addition to Bluetooth, which was incorporated into the Bluetooth standard as of version 4.0 in 2010. So one major difference is that Bluetooth Low Energy is obviously more energy efficient, as the name says, and this uses actually fewer channels, so only 40 channels with 2 megahertz spacing. So this reduces the overhead for switching. Of course, it increases the danger of interference a bit, but then it reduces the amount of energy that you have to use for switching here. So here's a table comparing Bluetooth and Bluetooth Low Energy. So the nominal maximum range of Bluetooth is 100 meters. Well, in theory, in practice, it's just very often just 1/10 of this. Bluetooth Low Energy runs on lower energy, transmission energy, obviously, so it's definitely lower. The data rates in regular Bluetooth are usually between 1 and 3 megabits per second. Bluetooth Low Energy reduces the data rates in order to save energy. So you have several different defined data rates between 125 kilobit per second and 2 megabits per second. Essentially, the application throughput is a bit lower than this because in the end, of course, you have some overhead that is deduced here. The number of active slave devices in the Piconet is restricted to 7 in Bluetooth. Bluetooth LE is more flexible and makes this application dependent. Bluetooth LE also updated security in comparison to Bluetooth. So Bluetooth has either 56 or 128-bit encryption, whereas Bluetooth LE always has 128-bit AES encryption in the most common mode, which is called CCM. It's robust, so as we've seen, we have adaptive fast frequency hopping for Bluetooth, and in addition to this frequency hopping in Bluetooth Low Energy, we also have checksums, so 24-bit CRC checksums attached to each packet, and also an additional 32-bit message integrity check. So this is able to catch more transmission errors. The wake-up latency in Bluetooth Low Energy is quite a bit lower, so it's only 6 milliseconds compared to around 100 milliseconds. And the minimum total time to send data is there's 0.625 seconds it is, and this will reduce to 3 milliseconds. The general network topology is a scatternet in both, and of course the interesting thing here is power consumption. The reference power consumption for Bluetooth devices can take up to 1 watt, whereas for Bluetooth LE, depending on use cases, it's between 1 centiwatt, so 10 milliwatts, up to half a watt. And the peak current consumption, accordingly, is also just half of what the one in Bluetooth is. Cellular networks were built obviously for the mobile phone infrastructure, but most of the cellular networks obviously are used for transmitting data now too. So cellular networks are called that way because the geographical distribution of such a network is split into cells. So as we see on the bottom right-hand side here, these are usually depicted by hexagons. Though of course, if you have a cell, it's essentially a circle, so you have some overlap, but the hexagons look a bit nicer. So inside of each cell, you have a transmission tower, so a mobile phone sender and receiver base station, which is responsible for covering that cell. And then, of course, in the next cell, you have another one, and these mobile base stations can communicate with each other to provide packet forwarding and call forwarding and so on. So this fixed location transceiver or mobile base station is, required for cellular devices. And of course, in order to make use of it, you need to have a contract with a provider. So usually in the form of a SIM card, which you can then, or which you have to use and enter in your IoT device. And of course, you have to usually pay for the contract here. So we've seen there's a number of different standards here, from 2G, which was introduced in 1993, to 5G, which was introduced 4 years ago. And we see different properties here. I'm not going to read all the properties, but what's interesting is that with original 2G, you had the data transmission rates over the net of just 9,600 bits per second, so around a kilobyte per second, which is obviously not a lot. And with 5G, theoretical data rates are expected to be up to 10 gigabits per second. So in this range of just like 25 years, we have such a huge development here, from 10,000 to 10 gigabits, so a million times faster. Obviously, there are some disadvantages to cellular. First, you have relatively high energy consumption. You probably know this when you're on the phone all day and browsing network over a wireless network. Then, your battery is dead after a day or even less. So energy consumption of the wireless radio is one of the largest contributors to energy consumption in a mobile phone. The other one is a display. And of course cost, because you have to pay for traffic on these networks, and sometimes this can be very expensive. Let's now move on to wide area networks. So low power wide area networks are ideal for large scale IoT applications where you, for example, have something like applications in a smart city where you want to distribute sensors over a large area of several kilometers. So, as the name says, low power wide area networks cover a large range, a long range from a few kilometers in urban areas to maybe 10 kilometers in rural areas, which enables effective communication in not only outdoor situations, but also in otherwise infeasible indoor and even underground locations. So it's a very useful technology for connecting devices. It's low power, so LP WAN is optimized for reducing power consumption. And the idea was that transceivers for LP1 can run on small, inexpensive batteries for up to 20 years, compared to a day of your mobile phone runtime. They should be low cost, so the protocols should be simple and lightweight, so they should be able to run on small 8-bit microcontrollers. So we wanted to have reduced hardware complexity and lower device costs. And we also wanted long range and a star topology here. So the star topology here means that we have reduced infrastructure and network costs. In LP1s, we distinguish between two node types. We have full function devices, which, well, have all the functionality that's required. And then we have reduced function devices, for example, just simple sensors that are maybe only able to just send and receive simple data packets. And, well, we can have these star networks. So we have a central hub, for example, that you put in a very convenient location, like up on a tower in your city when you want to have sensors distributed over your city. But you can also have peer-to-peer networks where you have point-to-point communication between nodes. In addition to these long-range networks, we also have new technologies for short-range network communication. And the standard that lies under most of these technologies you might have heard about already is another IEEE standard, and it's also of the 802 family, so it's wireless networking. And we've seen Wi-Fi was 802.11, and this standard we're talking about now here is 802.15.4. So this is a standard that specifies the two lower layers in our ISO or OSI 7 layer model. So the physical layer and the media access controls for low-rate wireless personal area networks, as it's called. So this IEEE 802.15.4 standard provides the fundamental lower network layers. And this standard is actually used by a number of protocols you might have heard about, like ZigBee, like ISA 100.11a, like Wireless Heart, like MyWi, like 6LoWPAN, Thread, and Snap. So the range is very comparable to Bluetooth, so it's about a 10-meter range. The transfer rate is a bit lower, so it's usually up to 250 kilobit per second. But if you want extreme lower power devices, which don't have high requirements for data bandwidths, you can even go lower and have reduced transmission rates of 20, 40, or 100 kilobit per second. Accordingly, you can save quite a bit of energy when transmitting on these lower bit rates. So we have these two layers that are defined in IEEE 802.15.4. One is the physical layer, which is responsible for actually transmitting data between communication partners. This uses a technique called direct sequence spread spectrum. So it's also using the parts of the whole spectrum to disseminate information. And this runs in two different frequency bands here. In Europe, we have one channel available in the 868 megahertz band, and worldwide we have 16 additional channels in the usual 2.4 gigahertz ISM band. So, in addition to Wi-Fi and Bluetooth, 802.15.4 is yet another technology competing for these frequency bands here that can be used by everyone. On top of the physical layer, we have the media access control layer. So this enables the transmission of these media access control frames. So the basic data packets that are actually sent over the wireless network. And this is then, of course, sent over this physical channel, depending on the frequency you configured. And this media access control layer is responsible for a number of things. So it manages access to the physical channel. It manages network beaconing, so saying, hello, I'm a new device on the network. It controls the validation of frames, so it checks the frame integrity of received in data. It guarantees time slots, so we don't interfere between different communication devices, and it can also handle the association of nodes to networks. So one of the protocols that's built on I802.15.4 is ZigBee. So ZigBee is a specification for, yeah, as it says, a suite of high-level communication protocols, and these are used to create personal area networks with small, low-power digital radios, such as home automation or medical devices, and so on. Uh, so essentially, ZigBee is simple enough to be integrated in something like an IoT light bulb, like the one we've already seen in the IKEA toll-free light bulbs. So this is quite a lot simpler and less expensive than very many other wireless personal area networks. And in ZigBee, we have three different classes of devices. So we have a router. So a ZigBee router is responsible for routing traffic between different nodes. Routers do not sleep, so they are always on in order to enable communication. Then we have a ZigBee communicator, which is a special form of a router with additional functionality. This is able to form a ZigBee network, so to assign channels to devices, to select the channels used, to provide devices with IDs on the personal area network, and also to address networks, and also maybe to interface all of this to the internet. And then, of course, we have ZigBee end devices, which do not route traffic, and then can also be mobile devices, can also be switched off, obviously, or run out of battery, and can join the network on demand later on again. So one example for ZigBee is something you can just buy right away in the next IKEA store, which is the gateway for the toll-free network. So this is actually a relatively complex solution that interfaces ZigBee to regular IP gate networks like Ethernet, Wi-Fi, or even Bluetooth. And to do this, you see the PCB of that device on the lower right-hand side, and we identify some of the major components here by color. So what you can see here, it actually has two microprocessors to handle this. So there's a EFR32 ZigBee controller, which is an ARM embedded Cortex M33 microcontroller, and there's an additional system on chip able to handle Ethernet and Wi-Fi by Broadcom. So this is another chip of the ARM Cortex family called R4. This is a very powerful device. In addition, it has some other components like flash. So, of course, all these microcontrollers need to load their firmware from somewhere. So that's what the flash is for. And it has a separate Wi-Fi module, which has this Bluetooth and Wi-Fi chip from Broadcom included here. So that's the yellow large thing under this metal cap you see on the PCB. Uh, Amazingly, this cheap device has a large number of functionalities, but not all the features are implemented so far as I know. So, for example, you can use the device with Wi-Fi 802.11, but there is no Bluetooth functionality enabled so far, even though the hardware would be able to support it. What would be possible with even the power we have in this device would be to enable functionality to directly control connected devices over the internet. So the idea would be that these devices could be powerful enough to run a small web server on their own, which you can then access from your mobile phone, and then, for example, switch on or off the light or the heating or whatever is connected there from somewhere outside of your house. Unfortunately, this is not enabled, so here you have to use cloud functionality again. So what this gateway actually provides is a link to Alexa and also Google Assistant, so you can use it there. But of course, then either Google or Amazon pretty much knows what you're doing in your home. Um, and these are very standard chips that are used here, so they're optimized for cost, obviously, because the whole gateway is, I think, around 500 kronas nowadays. And it's interesting to note that a very similar system on chip from Broadcom is also used in the Raspberry Pi 3 as the wireless and Bluetooth solution there. So this is a very common chip that is available, broadly on the market. And of course, in addition to the router, we have end devices. We've already seen the light bulb in the introduction before. So the light bulbs here are a family of what they call smart light bulbs and related devices. And they use a special protocol which is called the Zigbee Light Link protocol. So this is a protocol that sits on top of Zigbee and is just responsible for controlling lights. So you might think like controlling lights might be very simple, like I turn the light on or I turn the light off. So it's one bit of information per lamp. Why do we need a special protocol? Now, of course, you can do quite a bit more with a modern lamp. So, for example, you can have multicolor LED lamps here, so you can control the color. You can even control color cycling. You can, with monochrome lamps, you can dim them using pulse width modulation, or you can control the color temperature by enabling a mix of warm and cold white LED lights. So, the Zigbee Light Link is an open standards protocol that's aimed at remote control of everything that has to do with light. And these lights actually can also create a mesh network with each other. So without requirement for a central device here. So this means you can have a larger range. So you can enable one light bulb to pass on messages to the next one and finally to a router if it's required. In ZLL, there's two general categories of devices. So first you have light devices, and as we've seen, they have functionality to be switched on and off. They can be dimmable. They can be set to different colors if you have color LEDs, and also you can control the color temperature. And on the other hand, of course, you have things like light switches and dimmers, but also things that enable building automation for like office buildings. So in very many modern devices, you have something like an occupancy sensor that automatically figures out, maybe using an infrared sensor, if there's somebody in a room, and if not, it can simply switch the lights off between the lights because the lights probably won't be needed if nobody's in the room. And of course, you can do the same with heating and so on. And you can have remote control units to just control the lights in your whole house. And you can have, oh, well, of course, also all that stuff controlled from an app on your smartphone also. So usually the controllers are end devices and the lighting devices also act as routers, even though they only have a small microcontroller. But we've seen that's quite a bit of computing power for such a small light bulb already. And the good thing is that this protocol is made to be interoperable, so it's not proprietary. So we have standardized control message for all the functionality we've seen before. And we can also organize devices into groups. So for example, we can switch off all the light bulbs in a room or on a level of a building or whatever you can imagine. So this is a quite advanced protocol that's used in such a small light bulb already. So here's just an example of a possible setup with Zigbee ZLL. So on the upper left-hand side, we see that, we have, for example, a scene that connects a number of different light devices that then can be controlled. And all this control is happening over the ZLL control bridge. So essentially the gateway we've seen before. And this control bridge then can in turn be connected to your internet router. And then you can have something like an app on your mobile phone to communicate with the ZLL control bridge, and then the ZLL control bridge translates all the information coming from your phone, so either via a web browser or via a specialized app, into the ZLL packets required to configure your lights. So this is very convenient here, and on the lower right-hand side we have a comparison of ZLL to other technologies that might be used for home automation like BLE, Bluetooth Low Energy, and Wi-Fi. And obviously ZLL is lighting specific, so it's very optimized for just enabling automatic lights with low costs. So these light bulbs can be bought for around 100 kronas for the cheapest one. And essentially you have low cost, you have low power consumption here. Still the networks are scalable. It can have a high range due to every light bulb being a router in such a system. And the network formation is very flexible, so you don't have to do a lot of administration. And Wi-Fi, of course, takes more setup because you have to somehow enable the assignment of addresses and so on. And Bluetooth Low Energy has problems with scatter formation for longer ranges, for example. Another technology that's used for low power networks is an interfacing technology that tries to solve one problem. Now, the problem with IP-based networks on the Internet of Things is that originally all devices on the Internet used the IPv4 protocol. And the IPv4 protocol had one significant drawback. It was designed in a time when there was like a handful of nodes on the Internet, and the designers of the IPv4 protocol actually were pretty optimistic about the growth of the Internet and enabled the addresses to be 4 bytes long. So this means 4 bytes are 32 bits. We can address 2 to the power of 32 devices on the Internet with IPv4. So that's around 4 billion devices. Now, there's already 8 billion people living on that planet, and well, unfortunately, very many of these people don't have any internet access and any electronic devices at all. We know that in Western countries, we have like, yeah, large numbers of IP connected devices. I mean, if you start counting in your household, it will be at least a two-figure number, I guess, of devices somehow connectable to the internet. So the problem is that the IPv4 address range was just yeah, depleted and exhausted. So there were no more available IPv4 addresses. And if you need to buy an IPv4 address for your application, that can be very expensive nowadays. So the problem is, how do we solve this? Now, more than 20 years ago, people already anticipated that problem and introduced IPv6. So you might wonder, where is IPv5? That was an intermediate technology that never was made into a standard, so they continued with IPv6. And IPv6 extended the addresses from 32-bit to 128-bit. So with 128-bit, I guess you can address every single molecule in the Milky Way, which should be enough for the foreseeable future, I guess. The problem, of course, is that IPv4 packets and IPv6 packets are incompatible. So in very many places, you only have an IPv4 infrastructure, but nevertheless, you need more devices than you have IPv4 addresses available. So usually your internet provider only gives you one address for your router, and then there's a technology called network address translation, or NAT, that does the trick of, yeah, just translating a range of internal unrouted addresses to this one external address. But this is quite a bit of a hack. It would be much better if we would be able to use IPv6 directly, and especially over these low power wireless personal area networks. So the basic idea with 6LoWPAN is that we want to apply the Internet protocol even to the smallest devices directly, and even on low power devices with very limited processing capabilities, these should be able to participate in IoT. So 6LoWPAN actually defines yeah, specific functionality that's not in IPv6 that enables these small devices to participate in the IPv6 network. So especially special encapsulations and compressions of header to reduce the bandwidths and to enable IPv6 packets to be transmitted over IEEE 802.15.4 based networks. So a number of problems were to be overcome here. So for example, if you want to transmit IP packets over either 802.15.4, we have the problem that IPv6 requires a MTU, that's the maximal transmittable unit, so a minimum size of a network packet to be at least 1280 bytes, the maximum transmission unit. And whereas in 802.15.4 is only 127 bytes. So essentially, you have to split up larger IPv6 packets into smaller 802.15.4 packets and to reassemble them somehow on the other end. The other problem is in the address resolution. So 802.15.4 only has 16 or 64-bit addresses, depending on the mode it's operated on. So we have to somehow be able to translate these 128-bit IPv6 addresses to these smaller addresses on 802.15.4. And we wanted to have a parameter optimization. So usually IPv6 applications are built for high speed, but of course for IoT application, high speed is not that relevant. We rather want low energy and maybe also small code size for very small microcontrollers. Additionally, we also wanted to have methods for device and service discovery, so we don't have to configure devices on the network manually. And there's quite a number of additional functionality we're not discussing here, like interoperability, managing of addresses in the network, routing, and security. So 6LoWPAN is such a nice interfacing layer that is able to join this 802.15.4 technology, which was originally not intended to run IPv6 traffic, and this is then combined with modern IPv6 uh, communication, which then works around the problem of not having enough IP addresses for all your little devices on the network. There's a set of other alternatives for IoT applications. So I mentioned two here. One is Z-Wave. So that's a wireless communication protocol for mesh networks, mostly also used in the home automation area. Z-Wave is actually a proprietary protocol and proprietary hardware compared to the open IEEE standard. And Thread, on the other hand, is also IPv6 based, a low power mesh network technology, which is based on the 6LoWPAN standard we've seen before, so in turn on IEEE 802.15.4. Thread is not a peer-to-peer mode, so it requires the use of a connecting router called an edge router here. Thread, unfortunately, is not as open as it seems. So to be able to access specifications, you need to sign a non-disclosure agreement with the company that, or the industrial organization nowadays that standardizes Thread. Nevertheless, it's not an open standard, but if you want to take a look, there's an open source implementation of a Thread protocol stack by Google, which you can download from GitHub. So if we want to go to long range networks, again, we have LoRaWAN. So this, is intended to solve the problem of mostly infrastructureless communication, as we've seen before, outdoors as well as indoors. So compared to the short range solutions, now we have very low data rates here. And this can be like weather sensors that only send like small packets with a whatever temperature and air pressure every couple of minutes because you don't need that data so often. So you want to have a wide range communication and then you accept a very low bandwidth. We've already seen this is based on spectrum modulation technologies and can range up to the tens of kilometers, 15 kilometers usually, with only milliwatts of power consumption. So we have nodes that can run for 10 years of battery. So you see, we have network technologies for all sorts of different applications here. And it's interesting, especially also to combine these in larger networks, which you might need for things like smart city applications, which might integrate solutions like smart buildings, where you have some of the short range technologies and then integrate it with these long range technologies. For example, to get a weather forecast over your city to predictively control the heating of your building. So here we have, that's from industry, so they're actually trying to promote LoRa, but here's quite an interesting technology comparison again with all the important data on the different technologies and some more we have discussed here. So question when designing your IoT system is obviously which wireless technology to use here. This is really dependent on the use case of your system. So essentially, one driving factor is obviously power saving, but another factor might be cost, mobility, range, security, and so on. So there's no technology that's suitable for all application cases. Uh, you have a large number of standards. Some are public, some are proprietary, and sometimes, of course, the technology you want to choose or you have to choose is really dependent on whatever other devices are already available in your network. And sometimes you also have to build solutions to just bridge protocols from one protocol to another if you want to integrate technologies from different vendors. So this lecture might give you a short introduction of an overview of the available technologies. Choosing a technology in turn is dependent on so many factors that we cannot give a general recommendation here. So, in conclusion, we've seen a large number of different technologies, differing in throughput, in latency, in costs, in energy efficiency, in the operation mode, in the range, and so on. We've seen we have an adoption of convenient technologies from the PC sector like Wi-Fi and Bluetooth. We have cellular networks, which actually cost money to transfer data. And then we have very many IoT specific solutions, open versus proprietary standards. Most have in common that they're very energy efficient, simple, and also reliable. And we've seen mostly we can classify between short range and long range protocols. And we've also seen that this interoperability, which is really relevant for the Internet of Things, so being able to communicate over IP-based protocols, this is done using network protocol translation. And the common standard for this is this 6LoWPAN standard we've discussed. So as always, here are a number of references if you want to dig deeper. So these go from standards here. Unfortunately, things like IEEE standards have to be bought. They're quite expensive. There are links to different specifications for Bluetooth and for other network technologies. So if you're interested in digging deeper into one of the technologies, feel free to do so. If you want to experiment, there's quite a number of links like reference 10 and 11. Uh, that's essentially people trying to hack on the whole home automation hardware from IKEA. So please take care when you experiment on light bulbs because these are operated on just mains voltage, so 230 volts. So this can be very dangerous. So obviously uh, you have to apply precautions and power the devices, for example, only from a 5-volt device. And this is also mentioned in the hacks here. So if you want to experiment with this, please stay safe. So in the next part of the lecture, we will discuss the application protocols. So now we've discussed everything that happens on the network, how we transmit packets of data between different nodes, but we have not defined yet what's actually inside of these packets. And of course, we want to enable IoT applications that can communicate, that can control things. So essentially, in the next lecture, we're going to take a look at some of the standard protocols that enable IoT devices to talk to each other, which are based and can be based on the protocols we've discussed in this lecture. So that's all for today. Thanks for listening, and until next time. Bye.